Okay, welcome back to again the Zoom session on computer vision. The last lecture we started looking into the stereo vision. There are two aspects that we are looking at. One is based on the calibration. So there we have seen that if you take one pixel in one of the images among the two cameras from which you have acquired, okay, that will the possible sets you need to just look at a single line there and vice versa, right? So these lines are referred to as epipolar lines, and this constraint is also referred to as is in a way a hard constraint because it cannot go anywhere else for its correspondence. Okay, that is coming from the simple fact that a line here in a perspective projection forms a line. Okay, that's from where we put the hard constraint. So I guess Shashwat is now here, right?
Yes, sir.
Yeah. So you were asking, I was just thinking about your question. So you were asking, suppose if there is no disparity in the two images, what would happen to epipolar lines? That's the question, right? Let's
Yes,
think
sir.
of it this way. You have one camera here and other camera here. Okay. You kept them one on top of the other. So that is when what could happen? Well, there could be a shift in in the the y-axis, but in x-axis, what would happen to a point? A point will get mapped to so a line there. Okay, so one point here in one image, all possible points they will get mapped to a single point there in the other image. Is that not? So the locus would be in a way would be, I guess it would be just a point there. And you won't be able to in that case resolve what exactly is the height, because the both projections are in no way complementary to each other. So you have one point, but that doesn't help you to find, so the disparity is zero. So you can't find, it's not useful, you can't figure out any what exactly is the height at that given point.
Okay, sir.
No, does that make sense?
Sir, here the epipolar line will be actually a point in both the images.
See, what do we mean by epipolar line? You have, for example, in one image, there is one pixel, correct? And this pixel could be coming from any of the points in the z-axis. From, say, I have the like my optical center is there for this camera, and then there is a pixel here. There is a line passing through that. So any of these points on this line could contribute to a single point here, correct? And if you are looking at where this line would map to in the other image, that's what is your epipolar line in the other image. The locus.
Okay, sir.
So now the situation is, suppose I have one camera here, on top of it there is another camera. So all these points here also, if I am taking it, that's when I see no disparity. So what would happen? This is still a point here. Both are points. So there is not really any complementary information there. You are like both are blind, or both are looking, both are blind in the same direction, I would say. So it doesn't give you, but if you are interested in looking at what would be the epipolar line, I guess it would be a point.
So why a point exactly? Because since every point on this perpendicular line,
right,
will correspond to one more point in the projection space of the other.
Be a single point there. See, my image is like this. See, the camera is like this, right? So if this is the pixel at which all these rays are falling on. Okay. Now, how do I get the epipolar line? What I should do is, where this point would correspond in the other image. Okay, all these points. What is the locus of all the correspondences of these points in the other image is what I would look at.
Okay, it is the same point.
Exactly. It could be a same point if it is in the same thing. Suppose one camera is like this and another camera is like this. So that would be a different point then. So there will be a shift in the y-axis if the baseline is something not horizontal.
Yes, sir.
So if both are horizontal, means you have the same image price. That's all. So in that case, it would be the same point.
Okay, sir.
Makes sense, right?
Yes, sir.
Yeah. If you come across anything different, let me know. Okay, let's go back to our presentation. It seems it is giving me, you are already in another meeting. Do you want to leave and join this meeting? What is this? Hope. Yeah, it's still there, hopefully. Okay, good. So I think this is trying to, that was okay. Let it do that. Let me come back to the presentation part. Okay, so where did we start here? We have done, let me also turn off my video. Okay, good. So we looked at this epipolar things first. Okay, epipolar geometry that comes from the calibration of these cameras, and all that is telling us now for a point we need to search. Now the scenario is the search has been restricted now to a single line, across a single line. So that was the case with the epipolar constraint, and still we have to find out a mapping for it. Okay, now across the so somewhere on the line we have to do that. So for that, what we did now, so additional constraints have to be imposed for it to look at similarity and other things. So first thing we had looked at is how similar are they. So you could start with, for example, looking at the intensity of an individual pixel. Okay, that's mean square difference we have seen. Well, mean square difference is susceptible to variations in intensity, so you could go to normalized cross correlation. There could be noise, so taking a single point is not good enough, so you take a patch around that. So that's where we stopped it in the uh, last lecture. So these are all we have seen there. Okay, and this is the case where we have seen essentially the moment you are taking a patch, you are making an assumption that the whole patch has the same disparity. So that's how you are looking at the similarities there, right? So that those are the two extremes. Okay, so we had looked at disparity, and also the fact you are taking a patch around it is assuming the depth doesn't change too quickly. Okay, so now we would look at two more correspondence problems that you would make an assumption there. Is the first one is a uniqueness constraint. That means the matching is unique. Okay, there is only one matching that's possible among all the pixels that are there. One pixel cannot correspond to more than one pixel. Okay, so he is mentioning here up to one match. That means it can also be the case, also could be where there is no match at all. Okay, that's what he highlights that in the video lecture. So why do you call it up to one match? Why can't there be uh, why can there be a case where there is no match? Or let me put,
Occlusion.
yeah, that's right. So the image, that particular point is present or getting occluded in one of the image, present in only the other image. So that is when you would end up with the case where there is an occlusion. So if you look at, there is a huge literature on dealing with occlusions. This is a very critical problem to be addressed carefully. So wherever you see some leapfrog improvements, okay, jumps in the accuracies, that is where you would see usually occlusion being modeled more robustly or more accurately. Okay, so what it is saying you in other words is, suppose you have, this is the optical center, you on this image you have one point. Okay, this could either map, so this would have this locus. Okay, on this image assume that this is the epipolar constraint, it cannot get matched to 2. That's what it is saying. You might end up with not matching to any point, but at most you could match it to only one point. So this is well explained in this image. Suppose you have a scene like this. Okay, again you visualize them as if those blocks are coming out from your screen. Okay, those were the blocks, that is how it is there. And then you are, there is, this is the optical center for your first camera. And if you look at here, it is able to access a point here from this camera. And the correspondence epipolar line, if you look at it, should be, assuming in a case where this object is not there, would have fallen here, correct? But what you see here from this object, because this is occluding or this is obstructing it to go there, so it cannot have access to this region at all. So this region is occluded from this right hand side camera. So then if you try to find out where this point has mapped to in the other image, it doesn't make sense at all, is it not? So that's where this part is occluded. So that's something you yeah, anyway, we are not going to, we just had looked at how you impose constraints about the similarity, but occlusion we would be skipping. So simple, if you want a very simple case, the way you could think of is, if your normalized cross correlation is below a certain threshold value, okay, there is no value above a particular threshold, then you will not, you will stop looking for a match for it, okay, you just leave it that way. That's a very simple scenario you could think of, but there are very well advanced models for it. Okay, so is this figure illustrating you the same case here? For example, yeah, I made it, actually I should not have made it, I made it red, so it's giving a wrong impression there. Okay, this is basically green. Okay, you could see here what it sees is a object red, red, green, 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 and this red. On the other hand, what you have seen here is, in place of red there, you have green here. Okay, so that's essentially coming from the occlusion part. Similarly, this might, whatever this also, actually, yeah, this is trying to look at this part. Okay, so which is green here, but it could see only here, but what the correspondence looks here is red. So they are apparently looking at different objects. Is the occlusion part, is the problem clear? Anyway, we are not looking at solution for it. All we are saying is what could be the issues for it that needs to be addressed to get accurate accurate disparity maps. Okay. See, the next one is another constraint that is usually imposed is, if you see here the order of points, if you look at here, you call this as A, point B, and point C. So another constraint that would be usually imposed is, even after the disparity, these points will be in the same order. That's the assumption that is made, and sometimes this is okay, this is violated, and usually most of the commonly used methods would fail to deal with uh, opaque objects or objects where this order could change. When this order could changes, for example, then there is an object which lets the light to pass through. Okay, so for example, you look at this point A, this could these points, if it lets the light to pass through, okay, during in some regions, okay, and then it would be a problem. Suppose if it is a very yeah, opaque means it doesn't pass through, it doesn't let the light pass through, right? Opaque is not transparent, correct? So it doesn't pass through, it doesn't allow the light to pass through. So for example, then this point is hitting here, so that would come here. So this would corresponds to, okay, 1 minute, discard. Let me go back here. Okay. So assume that this is your point A. Assume that it doesn't let the light to pass through. You get A here. And now this point, second point is B, hitting here, coming back here. This is B. And this is C coming here. The same order is there. This is easy to handle, and this is how the assumption, while you are considering the disparities and other things, you will do. And suppose, assume this case where this is a transparent object, not an opaque object. So look at now, this A object here hits here, right? And then it could come to this point. This is A now, and okay, this is the point B. It lets it to pass through here, assume that, and here only it comes back. So this would become B, and C would be, here it is not letting it to pass through, so CAB it has become. Okay, This could come either in these objects or in cases where you have some peculiar shapes, like for example the shape shown on this right hand side, okay, where while you are looking from here, there is a small slit like passes here where it could come out, okay. On the other hand, it cannot come out here. So there you could see, for example, here it is A, B, D, and then this order would change here. For essentially, the order could change for a transparent, or there are some occlusions when you are looking from just one side. Okay, it's like usually one student might be, while you are sitting in the class, the head of one student might be occluding the one sitting beside him, but if you move aside from the other side, it would be visible there. But that, you look at in terms of the cameras, that could, when it changes the order, that becomes a difficult problem to handle. Okay, we are just saying the problem here, we are also not trying to attempting at answering that. Okay, and then uh, so if you take a very simple example to solve the stereo, that whatever we have done earlier, that's good enough. Where what you do is, for each pixel in a given row in one of the images, you go through the same row in the other image, and across that row you look at for the, you take a patch around that pixel and find out the normalized cross correlation there as well, and whichever gives you the best normalized cross correlation value, you assign it to that point. So that's a very simple thing. Okay, and then the other things, depending on whether your object, do you expect the ordering to be same or not, so those additional constraints could be imposed there. Okay, and this is actually, you could say it as almost like it became like this image has become like a logo of stereo matching. So the moment you say stereo matching, this is the image you would find it out in most of the places. Okay, you'll find out the link in the later ones. There is something called as Middlebury, very popular, MBURRYRB. Yeah, just need to check the spelling there. Okay, so this has a set of values, set of images that have been captured in the University of Tsukaba. Okay, so this is a very challenging image. So you would find it out in a lot of places. You could see here. So basically, you need to figure out the height information here. This, for example, you could see from here, this table lamp is before. Okay, and after that comes this that image of the head. Okay, that statue of the head, and behind that there is this table is here. Hope you all could see that table, and even behind that there is this whole camera stuff is there, and much behind there, okay, you will see all this, I guess, oscilloscope, these files and these things are there. So this is how now the goal is to find out which is the disparity map for it. Okay, and so by the way, they use laser based techniques to establish the ground truth for all these things. So you could see here in the similar order, see, higher the disparity, higher the intensity used for it. Okay, and that's how you could figure it out from here. For example, more or less the table lamp has higher intensity, okay, uniform almost. Then comes this head here, followed by this, and followed by this, and then anything, the other cluster of disparities, they are treating it as the background. So that's what the ground truth is, and on that they keep applying these methods. Okay, this is, as I mentioned, if you just simply do the algorithm that we discussed, all you need to do is, what do you have to do here? You take one pixel here, okay, and for that pixel you take the corresponding row in the other. Okay, I'm drawing it here, but assume here the right side image is there. Okay, another very similar to this image. So on that, you take the whole row there. Then what you need to do, so you take around a patch around it. Similarly, around this you take a patch around it, and you, for this patch, and you slide this patch across this row, and you compute for each sliding patch the corresponding NCC with this window, and you take that pixel as the mapping pixel for which you found out the highest normalized cross correlation, and then you compute the difference between those two, and that is what giving you the disparity. And that's how, if you do it, this is what you will get there, get the result. Again, they were using now, instead of using grayscale intensities, they are using the colors there. Of course, this is being high disparity, followed by this. This is anyway ground truth, so this is what is expected. Then followed by that you have the stable, followed by that you have this, followed by that the background. Okay, so those are the, so essentially they are thresholding it into 1 2 3 4 5. Oh, five. In fact, there is one more, I guess. This is another range that they are considering. Okay, 6 with that. So the front part of it, the slab kind of thing, which is coming, projecting towards us. Okay, so that's what you. It's not very bad. Okay, you could see that still that table is getting more or less there, but what you could see is around the edges there are a lot of issues there. That's where, and of course there are some spurious things within the object also are there, but still it's not a bad approximation there. Okay, it does a reasonable job. Okay, so far clear. Then we will see some more advanced methods. Is it clear so far? Any questions so far?
So why the blue thing is there?
Why the?
So in the window-based matching, what does this blue pixel correspond to?
Okay. Perhaps that's another disparity that yeah, that's a good question. I didn't realize that. Well, it is probably in their threshold. Yeah, good point. They are getting probably in the threshold some other value. Hmm. Hmm. That disparity is perhaps what is there in the original image. Let's try to make a guesswork there. So, what is there around blue is something, these areas are getting mapped into blue, but
So they are
that's
near
not
the
at all there
edges.
in the image at all, right? In the ground truth, it is not at all there, correct? So it's at another disparity. So those values are either shooting up, okay, are coming. I think it's very likely the case where it is shooting up. Those values are perhaps are getting to some extremes there, either a lower extreme or higher extreme, and that's which is not there in this image, perhaps.
Yes.
That's quite possible. So you are getting it in the dark regions. So yeah, I should have shown the two images side by side also. There will be slight movement, but again you just go to that, that's a very nice by the way, in computer vision, this Middlebury has those guys, they are like, again, the textbook that we are following, Richard Sizelski is one of the guy, one of the key members there for that Middlebury web page. Where they did is they have some training as well as testing images. So training, yeah, training not in the sense that you do in the machine learning as such. Of course, it includes that also. But where you know the ground truth. Okay, ground truth is given to you so that you could, yeah, it's essentially training. It's same. Okay, so and there are some testing images also, and then they have different measures to do that. Where and then if at all you are going to come up with a new method and submit it for a publication either in a journal or conference, first thing they would ask is validate your results in Middlebury web page. So you need to upload your results there in the specified format. Your for example, this ground truth, yeah, your results in the specified format similar to this ground truth, and it does validations in various ways. For example, or overlap, precision, sensitivity, and also based on the classifications that you have in terms of images. For example, images with occlusions, images with let's say illumination variations, and many other stuff are there. And then it gives the ranking there. So it automatically does that. So that's a gold standard. That's the bar. Anybody working in the stereo. Nowadays, it has become a de facto standard, default standard, that you have to submit whatever results you have got with your new method. You have to submit there, get that validation done, and it will show you in the real time, it will show you on the web page itself it will show you the results where you stand, okay, in different ways. In for example, challenging data sets, illusions, noise, and everything. Too many things are there. So yeah, this is a very well done and very well implemented web page where they do all these comparisons and other things. Okay, so far clear? Right. You could notice the algorithm that we discussed doesn't really look at all the pixels, the correspondences at a time. It's like you individually pursue for each pixel. Okay. Yeah. By the way, here you could see those two images, left image and right side image. Okay. You need to spend some time to, in fact, uh, hopefully I did not copy, yeah, unless from where I have copied, they did that. Hopefully these two are different images only. Okay. Do you see any differences between those two images? Any slight variations do you see there? Easily
No,
to
sir.
observe is occlusions, one showing more in certain regions where the other is not showing. Could anyone see something? Okay, if not, you need to check. Yeah, there is a possibility that from where I took the slide, if they have done yeah, it is possible. But anyways, you could see those images you could download from the Middlebury web page as well. Okay, yeah, yeah. Coming back, the coherence of mapping the pixels. Okay, we are not looking to match the pixels simultaneously or coherently, if not simultaneously. That's not done in the algorithm that we have discussed. Then there are quite a lot of methods doing it. Okay, this is again something coming in probably in the beginning of 2000. Probably this method again is there, dynamic, using dynamic programming. They were doing it. So this idea, we will just, this called as the shortest path algorithms, they use it to find out the mapping. Okay, and then more advanced ones are there with Yuri Boyko. This is again a landmark paper on graph kits. Okay, that they, yeah, unfortunately we won't be discussing at this point of time, but that would give you even more accurate results than this dynamic programming. But let me just give you some intuition about the way they are trying to do it here when they are doing it in terms of shortest path. So you look at it this way: you have this left image here on the y-axis and the right side image here. Now you keep those images such that, for example, this corresponds to, I think, yeah, these two would correspond here. And as you were mentioning, one of you were asking if they are same, ideally then this matching would be something, that correspondence would be the middle one. But then depending on where it is matching, you try to coherently match it by posing some constraints there. You use those, again you translate the weights, and there are other penalties, or the way you do them here is in a way that you end up uh, by solving this graph problem. Yeah, I know, I'm saying it very vaguely here. Okay, you would be in fact optimizing some energy function. Okay, that's what essentially is done here. Again, this also they will do it like a single scan line, but it is so I would so more efficient ways of doing that is using energy minimization formulations. Okay, I'm skipping that the methods where they use shortest path algorithms, but even more accurate ones would be using so this is again a landmark paper in PAMI, pattern analysis and machine intelligence. Okay, what I will try to do here is, I will not tell you how to solve this, that's the part of graph kits, but rather would give you some intuition about what is it it's exactly trying to do. Okay, so basically now see, one thing is, you assume that the neighboring pixels have similar disparity. Okay, that's a reasonably fair assumption, is it not? You all which are there surrounding that would move will have a similar disparity. So that's what the similar disparity would come under the smoothness term. So where you take a pixel So for I is your pixel of your interest, you consider all neighbors of I as, let's say, j, and you compute a smoothness cost, okay, which would be minimum when you have, for example, this row of let me call k could be a function where this would be 0 if k equal to 0, okay, and then the more the disparities, okay, they have different disparities, so assume that I could keep okay, any disparity if I choose, there are again different possibilities. This is just a very trivial case I'm mentioning here. This is otherwise, okay. So if you take a so there is a pixel of your interest, you take all the neighbors, assume that you computed all the disparities for each pixel, and then within that neighborhood, you know the disparity of this is, for example, you got it as 10, okay. Now you see how it matches with all the disparities of its neighboring pixels. If it is also having 10, for example, the neighboring pixel, you would encourage that because all are moving coherently, okay. So then you would not penalize it. So this energy you look at as penalty for some time, and you are trying to minimize the penalty. You want to get a solution that minimizes the penalty. So that is your smoothness term. Is smoothness term clear to you? So what is it that we have to find out at the end of the stereo matching algorithm? What should we find out? What
The
should we do?
disparity map.
Exactly, correct. Good. So here we are already assuming that we know the disparities and trying to minimize that, is it not? But on the other hand, how do you, so this disparity, you look at the data term now. This is again very similar to what we are trying to impose through our normalized cross correlation, okay. For the time being, you simply take a mean square distance. So you pick up that value of d, okay. This, for example, in w1 of I is so this is your pixel of interest that you are trying to look at. You make this disparity to be 1 2 3 4 and so on. You go there, and at that pixels, so you take for a given disparity, you know the intensity, you compute the difference, you take the square of that difference, you sum them over all. If you are considering just a single pixel, the summation part is not there, but this is nothing but the mean square difference term. Do you see that? And here this would pick up, this would encourage you to pick up a disparity, right? The first term would encourage you to pick up a disparity that minimizes the difference of it with respect to its intensity in left side image, is it not? So the data term would just look at the data of and then tries to find out, it will assign a disparity, that function would be minimum as and when it finds so a best match, then that disparity it picks up. The smoothness term is not worried about whether the intensities are mapping. It all looks at its neighbors and says that if my disparity is similar to my neighbors, I would go for it. If not, I would put some penalty. So these you could think of as the moment the second term is trying to be similar to the its neighbors, that would end up with having higher value here, right? So this is what it pulls it back. And the moment this is trying to impose the best match, if it is not having match with its neighbors, this will pull them in the other direction. So then you have a weightage for these things. Of course, you have written as alpha and beta, but you could think it as e data plus some beta times e smoothness term, and this is what your total data should be minimum. So that's what how you would try to solve it. uh, is this clear? This is the very important stuff. The formulation of energy is, at least that has to be clear, although we will not be going how you. So the second term requires knowing disparities. The first term, only when you solve it, you know the disparities, but you have to solve it both the terms together. That's the challenge here. Any questions so far? Is that clear to everyone?
Yes, sir.
Okay, good. So here, what would happen? See, in practice, what will be the problem is again, these kinds of formulations were there from quite a lot. At least even this method that began came in 2001, but from 80s itself, there are methods to calculate it. So the way they do it is, for example, you initialize this d with something, okay, and then with that d value, then you modify the d value such that this one you go to each pixel and look at changing this d to what other value would minimize this, okay, that you again take it and they do it in a way iterative way, okay. So basically all these methods would be, most of the methods earlier to this are either computationally very expensive to deal with, or they would end up with a being very sensitive to what values of disparities you are initializing your solution to. If you start with a different value of d, they end up somewhere else, okay. And at this point it's enough to know this is able to give you, irrespective of where you start your what initialization you started with, it would give you the same global solution, okay. That under certain conditions, this GraphCats method would ensure you or guarantee you that you would end up with a global solution. So suppose your energy function is something like, okay, if I draw it in 1D case, assume that it's something like this, okay. This is your energy function. So in the local solution, if you do it, what could happen is you come up with some disparities, and the moment you reach it here, you would see that energy function is a growing in both directions, and this corresponding solution you would start with. But your initialization is somewhere here. The moment the initial disparities you have taken is somewhere here, then it would give you the global solution, okay. So yeah, I have drawn it again. This is your uh, okay. So for example, this is the value of energy. So depending on where you take it, it could end up at different so for varying disparities, for example, this could be the kind of graph. So that would be very, so some of you who are taking some advanced mathematical courses would have dealt with convex optimizations. And then if you have a non-convex problem, how do you convert? You do some relaxation. There are quite a lot of approaches for doing this. They will so this is a classical optimization problem, okay. And then GraphCats is something that would ensure you that under certain conditions, you would irrespective of where your initialization would put you, you will end up with a very globally optimal solution, okay. That's what this GraphCats does, okay. And so with just this kind of formulation, okay, you could notice here this is a mean square error. As long as the intensity variations are not much between the two images, this should be fine. And a very simple, there is something called as a parts model. That's what, okay, I don't want you to confuse with the naming. So this is referred to as parts model. If they are having the same disparity with respect to its neighbor, you will not penalize it, otherwise you penalize it. Even with a simple model, these things could improve you to such an extent, okay. This is not possible even with the dynamic programming and all. They would still look at things at row wise. Here you could see this neighborhood you will impose both in the x and y, you take a patch, and throughout that you compute this smoothness term. So that would ensure, that would give you far better results than any of those dynamic programming stuff. And yeah, this is not at all a bad solution, right. This is where you would be ending up here. So that's what. And again, we are not, yeah, this is the web page. You please go through that, middlebury.edu. Again, they have not only stereo, for example, I think some multiple views, and there are other problems also. They have these kinds of evaluations for. So under the stereo, this is a very popular one. Okay, so to sum up here, there are still certain challenges. So the challenges, in terms of challenges, if you look for stereo vision, having low contrast, in other words, if you don't have any texture around the regions, this is again, you want to find out a match, but that being a uniform region, it could end up getting matched to anywhere. That's a problem. Occlusions, detecting which part got occluded and which part is common across is a very big challenge. There is a huge amount of literature, as I was mentioning, on occlusions, and that's one of a very critical problem to be addressed. Okay, and then some reflections and other things are there, specular reflections, which is causing you problems, are inconsistencies across the two images. That's something is still a challenging problem. And another challenging problem is, of course, the baseline being very large, that also the amount of changes, that appearance changes that you could observe, would become minimal. That's a problem. And of course, you need to calibrate first to get these lines. That's not as simple as, we haven't in fact gone through the calibration. All that we have seen is just, we have seen enough thing to understand what it means by epipolar lines. Okay, and where to look for the matching. That's all we have seen. But there is a lot of things we need to understand there to make the calibration, such that for one line here, you get exactly line, you will figure out what is that epipolar line here. But if somebody makes a calibration error, the whole thing gets screwed up, of course. So those are the challenges there. Okay, with that, we are done with so let me come back, stop share here. Okay, yeah, so with that, we are done with stereo matching. And any questions there?
Sir,
Yeah.
sir, in portrait mode in cameras, they use portrait mode
Okay.
in like the latest cameras and mobiles.
Okay.
They use the stereo vision, you know, sir. In Google Pixel to XL and other new
Okay.
phones.
Yeah, that's possible. Usually, I'm not very well versed with the what exactly how they are doing it. See, suppose if you are using a stereo thing, usually what should happen is
There'll be at
there
least
should
two
be,
cameras inside.
yeah, there should be not only two cameras, there should be some distance between the two cameras.
Yes.
That's one thing. And then to getting the 3D information, stereo is not the only way. Stereo, this whatever we discussed, the so-called stereo of having two cameras is not the only way. You could, in fact, even if you are moving your camera in a systematic way, okay, then also it's equivalent to capturing the same image from two different views, is it not? See, I could have two cameras side by side, okay, with some baseline distance, and capture it, or else I capture this here, assuming that scene is not moving drastically, or I could somehow compensate for it. If I move the camera and take it here, then also I could get the 3D. Am I clear? So that's also in effect is equivalent to acquiring. So there also you could look for like you could identify how much is the disparities and all. So to put it slightly differently, we have seen shape from, for example, the texture, and similarly shape from motion is also there. So the you could somehow compute this motion that you are doing here using the accelerometer or whatever is there inside. Using those sensors, you could compute the motion, and the moment you are able to compute the motion, and if you look at how the objects with what distance they are moving and other things, there also you could compute the stereo. So this is my wild guess. I have not seen it or used it where they are doing the 3D from a mobile, but they might be using multiple cues, not necessarily the stereo thing. Because stereo as such is acquiring is very complicated. Actually, running the algorithm on the already calibrated data sets is much easier. I remember seeing some of the researchers there at EPFL doing the all setting and calibration, and then acquiring and then making those lines and all is a very complicated thing. So I'm not very sure you would be able to do that as if you are doing the cameras thing, but rather they might be using the motion. So so earlier also we have the optical flow. Do you remember? There we have seen one cube is moving, right? And then if you are looking at it, those objects which are closer to you, then they would be
Will
moving
have more
faster,
motion.
right?
Yes, sir.
That motion, yeah, motion estimation. So once you know, so those which are closer, since they move faster, if you somehow could know how the motion vectors are there, then you could interpret the 3D.
Sir, the portrait phone and a mobile phones, I don't think it's stereo because my phone only has one camera,
Okay.
and
So
that also
yeah, I
somehow
too
has
don't
put.
think that they will do it. See, if they are, my guess, as I was mentioning, is that they are using shape from motion. That's what they would use. So, for example, once you keep the camera, probably, yeah, again, I should have at least seen the camera and talked, but I'm just making a guess. If you are moving your camera and then you know any objects, then you take camera you are moving. So from one frame to the other frame where you are moving, okay, this is also comes under shape from video also, okay. So that once you compute the motion and look at where they are matching, from that larger the motion, the closer the object, so you assign a certain depth to it, and slower the motion, the background would hardly move, which is very far would hardly move. So that you would say that they are on the back side. So that's how you compute the depth information.
Yeah, okay.
Yeah, good.
Sir,
I'm convinced even you could develop some apps here.
Sir,
If this is, yeah, sure. Yes. Someone was asking.
sir, like in dual camera, it is not of stereo vision, sir.
Which one?
One is for taking the image. One camera is for taking image, and second camera is for depth, collecting the data of depth information.
Okay.
It's
Yeah.
like if it is a dual, if it is a dual camera, they are not of kind of stereo vision. They are, one will work on image and other will work on depth
Okay.
in phone cameras.
Oh, is it? Yeah. There is something called as this Xbox and other things. I'm sure some of you might have played those games. So that is
the
where
Kinect
we.
one.
I sure some of you have played, right?
Yes, sir.
Yeah, good. So there actually they do this depth sensing. So for example, you would be playing football and other things you could play, or even the shuttle and other things you could play. You need to initially do some calibration. It will ask you to run here or walk to the front and to the back to the squares it is displaying on the screen. Okay, then it calibrates it, and then you could play all these games. Xbox and other things. X Connect also used to be there. Now it got modified into some other stuff. So there they use stereo, but the phone I'm not very sure. So they might be, yeah, I'm not up to date with that. So they might be using, but nevertheless you could in fact write your own app doing it. And if you search, there will be definitely some apps doing it, where all you need to do is just move it in a particular order, okay. And while you are moving it, as I was mentioning, if it could, or maybe you need to figure out in which direction you have to move and other things depending on the context. And then from that you could you could do an optical flow based approach. To optical flow is good enough because it's not like you are suddenly moving to some other plane. The motion is happening smoothly. So use optical flow, figure out the motion vectors. Depending on that, you could say it, okay. And then you could use other things also. For example, this lighting is something we would use it. So people could perhaps be using the illumination also. So the first introductory class from shape from X, if you recollect, so we were saying there shape from shading, right? So that also could be used. Perhaps multiple things could be put together.
Sir,
Yes.
sir, we could also vary the focus from in a particular range and then acquire many
Exactly.
frames, and then
Correct.
for the particular object we can just focus on that frame. We can
That's
do
true.
like that also.
Only thing here is you might not be. So here there will be again. Again, I'm not an expert here. There is something is the real zoom and an optical zoom. There is something different is there where the real. So that probably more than the camera. If you have this proper camera rather than this phone, if you have a control over it, so then we have discussed about the field depth field, right? or which you get it well. So those things, and then you need to figure out what is it that got blurred. So you should use some algorithms that will be able to tell you. Again, that's not very difficult, although we have not discussed it. You could look at some statistics of the region, okay, and then it would tell you whether the kind of statistics is a very steep Gaussian or a very distributed kind of Gaussian. That would tell you whether there is, see, if there is an edge, you could expect around that region. If you take a small patch and look at it, you will see a sudden transition there, kind of, right? If it is blurred, you have a Gaussian with a large variance, right? So if some object is in focus, that's what that range you would see it to be very clear, so with less blurred. So that would tell you, also help you with figuring out whether that given object is closer or far away. That's true. But with the phone, I'm not very sure how good we could do it, because you don't really have a control. Yeah, maybe some app where you could control that zoom parameter allows you, perhaps you could do something there. But my wild guess is that perhaps using things like shape from motion would be much easier, because in these cases you need to also have some good algorithms to first, in the first place, to control the blur, to control the focal length, okay, and in the second case, to figure out, like, to determine which region is blurred and which region is not, okay, which we do it quite intuitively, but that's something you need to use the right algorithm there, appropriate algorithm there. Yeah, then in principle it is possible. Good. So any other question? Okay, then we will wrap it up, the computer vision course with this. Okay, so all the best. Hope you enjoyed this course, and then those final years. So I am sure I'll see some of you guys again in the next final year. Okay. Yeah. Any other questions before we sign off? Any other comments? Okay, then we will stop it here, right? I'll just let me